So welcome back. And the discussions today are going to focus mainly on Boltzmann machines and how we can implement them. And then we are going to, at the very end, if we get time, we're going to start with variational autoencoders, which is, in many, many cases, the more interesting method, which then, after that, we are going to discuss diffusion models, which are perhaps even more interesting. Now, the reason why I focus so much on Boltzmann machines is that if you have the basic understanding of the key elements here, like the Gibbs sampling, the Markov chain Monte Carlo part, which is essential, because we are going to calculate expectation values. And the calculations of these expectation values are done with stochastic methods like Markov chain Monte Carlo. Now, the other thing which is very important for us is what is called Gibbs sampling. There is also the alternative to use metropolis samplings, which is the standard approach which is used in Monte Carlo Markov chain. However, that becomes inconvenient for us because computationally it's going to require many more cycles. So Gibbs sampling is the way to do the sampling, which is a kind of standard way. And you will encounter that when we discuss variational autoencoders, diffusion models, and many of the other generative methods. So what I wanted to do now is to have a kind of a quick repetition of what we did last week, because that sets the scene for the introduction of Markov chain Monte Carlo, MCMC, and Gibbs sampling, which is actually the engine behind these Boltzmann machines. And then we are going to look at how we can implement one of the simplest possible types of Boltzmann machines. And I have provided you with a program I wrote, which is NumPy, and there's a similar one in PyTorch. And then at the end, there is an example on how you can actually use the very exciting MNIST data and then produce new images based on the probability which you have trained. So when we're done with this, then hopefully you see the basic machinery behind a generative model. And when we then move to variational autoencoders, we are going to change slightly some of the ways by which we do the optimization of the probability. But Gibbs sampling and Markov chain Monte Carlo are going to be key elements. Now, nowadays, people also use something which is called Langevin sampling, but we will not cover that one. There are links in the Jupyter notebook, which you can follow if you want to, and then get to the basic machinery of Langevin sampling. So what I'm going to do now is simply to switch to the whiteboard and then remind you of some of the things which we did last week. Actually, the beginning of this Jupyter notebook contains a repetition from last week. And then we are going to go back to the Jupyter notebook when we look at the Gibbs sampling and why this is interesting. And then finally, we are going to look at the codes and then start looking at variational autoencoders. So that's roughly the scheme for today's lecture. Okay, any questions so far? So let's switch to the whiteboard and remind ourselves a little bit of the things which we did last week. So in our case, when we are dealing with this type of methods, what we actually end up doing is that we want to optimize a probability distribution. Now, this probability distribution is assumed to be the result of independent and identically distributed stochastic events. So what we did last week was simply to define a cost function, L, as a function of x and parameters theta, which is then given by either plus or minus log of a probability of x of theta. And this probability P of x of theta is then typically given as the product of the individual probabilities. So we would have some x of I, which is then part of a domain X, And then we have so I hope you see the distinction between an uppercase letter and a lowercase letter. So these are the individual probabilities of the different events. So this is the basic assumption behind the probability. Now, if we look at all these methods, whichever method we choose, what we want to do is the following. So we have some data set. So let's call this domain X for the data set. So this is our X. This is the data. Now, this X, what we want is this probability distribution, which is the model for the data. So we want then to link this with some latent space. So I'm going to call this latent space. So this reminds us what we did with latent or hidden space. And here we have a set of events, H of J, which are also stochastic events. And there is a probability distribution. So we want to link this X with the latent space. And hopefully this latent space conveys some effective degrees of freedom. Now, for Boltzmann machines, these are called the hidden variables. And they give us more degrees of freedom when we are going to fit a function. So essentially, Boltzmann machines is a kind of neural network. But instead of training a function which reproduces the data, we train a probability distribution, which we then can use to generate new data. And with a probability distribution, we can also estimate standard deviations, errors, etc. So what we want then is a transition here, which we will call a probability H given X. So this is what we last week called the conditional probability. So we reminded you of some of the basic elements of statistics. Now, from this one, we can then train a new probability, which is a new conditional probability, like this. And that gives us, finally, the final distribution, which is going to be our P of X of some parameters theta. Now, there is an assumption that there exists a probability P tilde of X. This could be the exact probability which describes the stochastic data X. However, we don't know that. So what we are essentially doing is to make a model. So there is an underlying assumption that there is such a probability P tilde of X. It could be a Gaussian, which describes the data, but we don't know that. So what we are doing then is that we are, through the usage actually of Bayes' theorem in variational autoencoders, but also in diffusion models, we are actually trying to link the data set and the different probabilities so that at the end, we get this object here. So this P of X of theta is the object we want. So that means that just to quickly remind you, the optimization problem. So these parameters theta, the optimal ones, it can be either a maximization or a minimization problem. So you know that the log function, if it's positive, this is a concave function. If it's negative, it's a convex function. So you can choose what you prefer, maximization or minimization. So the starting point is that we want to maximize the probability. Nobody wants probability zero. We want something which obviously maximizes probabilities. And what we are then, if we do that, this is the quantity which we want to optimize. And this is for theta, and theta, typically real parameters, and we may have something like P parameters. Now, what we have is a model for this probability distribution. So these individual ones, which we put up here, the basic model is that we have a P X of I of theta. This is what we want, but this is something which we would compute from the probability which also defines the hidden or latent variables. So that means that we are summing over all these latent variables, and these are elements in a domain H. And then we have this P of xi of theta, sorry, not that one, normal comma, hj, and theta. This is what we call the marginal probability. This is what we want. We don't want a probability which also involves the hidden degrees of freedom or the latent degrees of freedom. They are used in the optimization for us. And hopefully they can reveal some underlying features which are general to the system. So if you remember back to what we did with the autoencoders, we had this latent space, which was actually us reducing the degrees of freedom to some specific effective degrees of freedom. And when we had those, we could reconstruct the data which we put in. So in a way, this represents, in terms of Boltzmann machines, some kind of additional degrees of freedom for the optimization problem. So this is what we call the marginal probability. And what we did last week is that this probability here, x of I, is given by a model of theta, is then given by f of x. This is a function, which is our model. And then we have an h of j of theta divided by a function which does not depend on x and h. And this is a normalization factor. And for those of you who have done statistical physics, this is actually now a sum over all the xj's and hj's of this function f of xi hj of theta. And this is a difficult quantity, the one which also is going to lead later to us introducing Gibbs sampling. So a quick reminder for some quantities which we also are going to introduce. Last week, we introduced the product rule from statistics, and that allowed us to define the conditional probability. So let me remember you that one. Condition, and we are going to use this when we are going to set up variational autoencoders. So the conditional probability is the probability of x given h, which is then given by the probability of h given x, and then we have a model here for p of x, like that. And this is something which is then used when we are going to set up Bayes' theorem. And the conditional probability is actually the one which you will see when we go back here to variational autoencoders. When we link the latent space with the final probability, we're actually going to need this quantity here. I'm coming back to some of these basic concepts, and you will see that more clearly when we are going to look at variational autoencoders. So the reason why I focus so much on Boltzmann machines in the beginning is also that this gives you a feeling of what generative methods are. And from a pedagogical point of view, it's perhaps an easier entry point. Okay, so that's my bias when it comes to these Boltzmann machines or energy-based models. Now, the whole thing with this function, f of x, so what I'm going to do now, and I have to be a little bit careful. So this p of x I and hj and function of theta, I'm just going to replace that one with a p of x of h and theta. And you could think of these as vectors. So they contain now many different types of variables. That means that the probability, this function which we have, p of x of h of theta, is something which I will define as f of x of h of theta divided by z of theta. And z is independent of x and h because we have summed over all the degrees of freedom. Now, this function which we are setting up now, this f of x is our model in f of x. So this is the function which we want to train in order to produce this probability distribution. And this f of x, in the simplest case, is the following. So I'm going to set up an example here, which is called a binary-binary Boltzmann machine. Binary-binary. And we are going to call this for a restricted Boltzmann machine. So let me remind you of this Boltzmann machine. And the last one is something which we are going to use the acronym RBM for. And binary-binary is going to be BB. So that means that a single xi takes two values, 0 or 1, or if you prefer, -1 and +1. This is up to you. This depends on the system which you're looking at. And then similarly, h of j takes the values of 0 and 1. So let's now look at a case where we have two hidden nodes. So we have an h0 and an h1, and then we have an x0 and an x1. So this is our system. And that means that we have n equal 2 here and m equal 2. What this means is that I can have the following input values. So I can have 0, 0, because it's a binary system. I can have 0, 1, and I can have 1, 0. And at the end, I can have 1, 1. And the same applies to this case as well. So what you see now for this binary system, I have 2 to the n possibilities here, and I have 2 to the m possibilities here. So these are the configurations. And this is something which we discussed last week as well. So this one connects with this, and there is going to be a weight, which we call 0, 1. This connects with that one, and that gives a weight 1, 0. This connects here, and it's a weight 1, 1. And then we have this one, which is a weight 0, 0. We have a new parameter, which plays the role of a bias, which we call for B. And then we have A0 and A1 here. So with that type of model, what it means is that if I look at the summation for the partition function of Z of H, this is something which we wrote in a generic way as the sum here over all the possible configurations X and H of F, of X, of H, of theta. This is something which we would have to rewrite in terms of X0 sum over 0, 1, X1. So these are now configurations, 1, 0, 0, 1, etc. So these are the two possible nodes which we have. And then we have H0 is equal to 1, 0, 1. These are the values. And then I have H1 is also equal to 0, 1. And then we have finally the function x of I, h of j of theta. So we are summing over all these possibilities. So if we look at the function which we have then, this typical model for the binary-binary case, the simplest possible model, and this is the one which we have encoded in the examples you find in the Jupyter notebooks. So the binary-binary model is then going to be given by a function where I now have my f of x of h of theta, which is given by a function, and I can have a minus sign here. So I can have an a t times x, these are vectors, plus b of t of h plus x transpose w of h. And this is actually this function a of t of x plus b of t of h plus x t w h. This is the same as a sum over I equals 0 up to n minus 1 of ai xi plus a sum over j equals 0 up to m minus 1 of bi hj, and then finally a sum ij of xi wij and hj. So this is the binary model where the x's takes values 0 and 1. The a's and the b's and the w's are real parameters. And the a's, the b's, and the w's are the parameters we want to optimize. So if we just put an insert here, so theta is actually equal to a, b, and w. So where w is a matrix. So these are the parameters we want to optimize. This is a typical example of something which is a Ising model lookalike, for those of you who have encountered the Ising model. Okay? We went through many of these things last week as well, but I just wanted to repeat them so that you see that when we now are performing the sum over x and h on top here, it actually breaks down to the sum over the input nodes and the hidden nodes. So we would typically call, in a Boltzmann machine, this is normally called the visible layer, and this is called the hidden layer. And if you go back to this image which you have here, the hidden layer is then represented by this latent or hidden space. And at the end, this is what we want. So when we are going to calculate the final probabilities, this is the probability we want. But in the training, we need to calculate the derivatives of the, let me just bring it back here. So we need the derivatives of this function here. And what we found last week is the following. So let me just quickly remind you of what we did last week. So the function we are going to optimize leads to a gradient over these parameters, theta, of log of p of x of theta. So this is a function we are going to optimize. And what we found last time, so this is just a repetition from last time. So we have x, which is in this domain of possible events. And then we had the delta theta. And then we have a log of this function f of x of theta minus the next function, which is an expectation value of the derivative of log f of x of theta. And obviously we want to drive this to 0. This function here is actually given by the sum over x element in x, and we have a probability p of x of theta multiplied with log of f of x with a given theta. And this is something which we are going to approximate with Monte Carlo sampling. So this is an expectation value. And that means that we are going to have a loop over Monte Carlo samples, MCS. And then we have a sum from I equal 1 up to the number of Monte Carlo samples. And this is going to be us evaluating this function here of an x of I as a function of theta. So this last object is the one which normally causes problems for us. Now, what you will see in the literature is this normally is the first term is called the positive phase. So this depends on us having chosen to use the maximization. So now I have taken plus log. If you take minus log, you will get a minus and a plus, okay? So it's up to you to choose whether you do optimization or maximization. So typically what people plot, when you look at this function here, they normally, when they look at the optimization, you will have the difference between these two terms. And clearly, this can be negative or it can be positive. And the evaluation which you have obviously depends on the model f of x. So you will often see that this term is called the data. And this term here, no, sorry, I put it on the wrong one. This is called the data part because f of x, even though it's the model, it's driven by the data. And this part here is often called the model part. Now, when we are going to do so-called variational autoencoders, we are not going to deal with this function. We're actually going to use something which is called the Kullback-Leibler divergence. And that is an additional way of performing the optimization. But what you see here is the standard equation for the optimization of a Boltzmann machine. Okay? Any questions so far? So before we look at the basics of a Boltzmann machine, of a Markov chain Monte Carlo, so the last part, so let me just remind you this. So the last part, the last equation is evaluated using Markov chain Monte Carlo. And this is normally written as MC squared with, and as you will see later, Gibbs sampling. So I'm going to come back to this. But first, I wanted to set up some of the basic equations which we have to program if we are setting up a binary Boltzmann machine. So let's do that. And you will find everything in the lecture notes as well. So let's now look at the binary Boltzmann machine, okay? So a PBB, and this is a function of x, h, and theta. And if we now use that model which we had, this is going to be given by 1 divided by the partition function as a function of theta, where we now have summed up all the variables x and h. And then we have e to the minus, and then we have a sum over I, and I'm just going to skip the limits. So this is a I multiplied with xi. There is a sum over j, and then I have a bj multiplied with hj, and keep in mind that x and h takes values 0 and 1. And then we have the next term, which is just an ij, and then we have xi, wij, hj, parentheses. This is the quantity which we would simply write as 1 over zbb of theta, and then e to the minus, and then we have this function a tx plus b t transpose, these are vectors of h, plus x transposed w h, and h is now, the w is now a matrix. And the partition function zb is actually us just performing a sum over x and h, and that gives us this function here. Okay. Now, one thing we can do, which actually the final probability we want to have, and I wanted to give you the basic mathematics here, so you see how we reach an analytical expression for the final model. So what we want at the very end is actually this quantity of x of theta, which is then equal to the sum over all the h's. And now I'm writing this in a little bit more compact way of x of h of theta. Now, this is something which we can sum up. So let's do that. And I want to give you the analytical expressions, because then we have the expressions which we are going to program when we implement Gibbs sampling. Now, one thing you see now with Boltzmann machines is that the model which we have chosen, which is this one, is a model which is actually going to give us nice analytical expressions. However, if you want to complicate the model, suppose your variables, the input variables, are not given by binaries, but they are continuous variables. Then you would have to change the expression for the x's here. You could replace that one with a Gaussian distribution, and that gives you a little bit more complicated mathematics. So in the lecture notes, in the Jupyter notebooks, you will find an example of a binary Boltzmann machine and a Gaussian binary, which you can actually evaluate analytically. So then you have analytic expressions which you can program. If you don't have that, if this function which we put in here is given, for instance, by a convolutional neural network, then obviously the calculations of derivatives, etc., is going to be much more complicated. And then you have to use automatic differentiation typically. But for the simplest cases of Boltzmann machines, you can actually do this analytically. And the program, which you will find in the Jupyter notebook, simply encodes this expression we will derive now and Gibbs sampling. So it's the Boltzmann machine itself is actually pretty straightforward to set up. But let's go through the mathematics here. So if you look at this expression here, then this is something which we can rewrite. So I just wanted to go through some of the basics here, and then we are going to go back to the Jupyter notebook. So this is a sum over h, and then we have e of minus, and then we have a of t of x plus b of t of h plus x and h. So when we look at this sum here, the whole thing now is that this is equal to 1 over zbb. And then I have I can single out because the term with a of t of x does not depend on h. So we can put it outside. And then I'm going to have a summation here over all the h's. And then I have an exponential and with minus. And now I have a sum over j. And then I have a bj plus. And since I'm not interested in the x's, I'm going to introduce a notation here where this means that I'm looking, since W is a matrix, so I'm multiplying a vector with the rows of the matrix. And this is just indicated by this X here. But then I have a J multiplied with H of J, like this. So that's the term which I have to evaluate here. And I know that this one is something which I can rewrite in the following way. So this is the same as 1 over ZB. I have E minus A of T of X. And this is something which I now can rewrite because these are exponentials. So I can rewrite this simply as a sum over all the J's from 0 to M minus 1. And then I have E of Bj plus X transposed W times Gj times Hj here. Are you familiar with that? Because these are just exponentials. And for each one of these sums here, there's a B1, there's a B1 there. And these are just some exponentials with a sum in, and I can write them out as products. So this is just a rewrite of the exponential, which contains a sum as an argument. And if I do that, then I can actually rewrite everything here in a very compact way. So this gives me the following expression. So this gives me 1 over ZBB. And then I have e to the minus a t of x, because I'm summing up. I want the marginal probability. So I have the sums over j, and I have m minus 1 nodes here. And this is then given by the sum over the different hj's. And then I have exponential minus, and then I have bj plus x transpose times the matrix and the right row elements and j columns here multiplied with hj. And now we know that the hj takes values only of 0 and 1. So that means that this sum is a sum we can evaluate because it's just 0 and 1. So that means that what I end up with is the following expressions. 1 over z bb, and this depends on the parameters theta. And then I have simply the product of the following expressions. E of minus at times x, and there's a product over all the hidden nodes, m minus 1, and this is given by 1 plus e of minus, and then I have bj plus x transpose times j multiplied with h, with just 1 here, like that. Because it's either 0, So if this term here is equal to 0, then this just gives us 1. Then if it's equal to 1, I simply have the second term here. Okay? So that's part 1. Now, I can do the same for the hidden nodes. So this is the marginal probability. At the end, this is what we want. And I can repeat the same exercise, and I can get the probability of P, of BB, of H, given theta, because I will need these quantities as well. And this is something which just becomes 1 over ZB multiplied with E of minus B transpose times H. And then this is multiplied with a sum over I up to the number of visible nodes. And then I have 1 plus E of minus Bj plus, no, sorry, not Bj, but Ax, Ai plus, and now I have Xi times Wi, and then I'm hitting the right column here, multiplied with H, like that. And that's the next expression which we have. So another thing which we can calculate, and I'm putting that up because we need that in the Boltzmann machines. So when we are going to simulate the RBM, we need to have a probability for when the node is on or not. RBM with probabilities for HI on or off. So we are going to say that it is on when HI is equal to 1, else it's off when Hj is equal to 0. So what we need then is the probability, what's called the conditional probability. So all these kind of concepts which we developed last week come back because we need to encode them. So this is the probability. So instead of having you can think of this as the activation function for a given node. But now we are using the Boltzmann probability to say whether this node fires or not. So in a way, we are training a probability distribution, which is a more realistic way of defining the activation function. Think of these conditional probabilities as the activation function for a given node. So I can do the algebra and you will find all the details. So I'm just setting it up here, but we need a conditional probability, PBB, for Hj equal to 1, given all the x values. So that means that we are summing over all the x values. Now, the nice thing with this binary is that you get analytical expressions. So that's going to be given by 1 divided by 1 plus E of minus, and then I have Bj plus X transpose, all the X values, so we have to perform that operation, multiplied with J. So the specific column, which then refers to the value H or J here. And then we know that since we only have 2 cases, then the case with X, now Hj equal to 0 is just 1 minus this one. So that means that PB, and these are quantities which we need to encode. So in the code, you will actually find these explicit expressions. If you don't have these simple machines or models, then you would have to calculate these derivatives or these probabilities actually numerically. But now you have nice analytical expressions. So we would have Hj equals 0, which is simply 1 minus this other probability. And that's given by 1 divided by 1 plus E. And then it's a plus Bj plus X transpose times W, and with a column element J here. So that should be a parenthesis here. Now, we can do the same thing for the X's. So we also need for the x's of xi equal to 1, given all the h values. And this has a similar expression, except that now we get 1 divided by 1 plus e of minus, and then I have ai plus, and then I have this omega I, and I have to transform this omega because that is a vector now. And so I need to do the transpose here. So let me rewrite it a little bit better. So this is wi, but I need to transpose it in order to multiply with the h values, like that. So h is a vector now. And then I have similarly the pb with xi equal to 0, given h, which is simply 1 divided by 1 plus e of ai plus wi transpose multiplied with h. So these are the expressions which we need to set up in the code. So you see the basic machinery here is that instead of you using an activation function like the sigmoid, tan-h, or any of the other activation functions you've been using in standard machine learning, in neural networks, etc., you're now actually using the probability distribution, and you train that so that every time you have new parameters, theta, then you have a new probability which tells you whether the node fires or not. Okay? You see the basic difference between, so you could actually use something which is called Bayesian machine learning, where you replace the activation functions with a probability model in a neural network. That becomes, however, pretty heavy to train because it's much easier for you to just run with an activation function, like a sigmoid, which has a simple analytical expression. Here, we are training a probability which tells us whether the node fires or not. Now, if you have a Gaussian, then you can actually replace these AIs, which we have here, with a Gaussian, which is instead of binaries. Now, the thing which is interesting for us, if you now look at the technicality in the calculations, when we are looking at derivatives. So when we look at the derivative of the cost function of L of X of theta, one of the quantities which we end up having to calculate is actually this one, of d of log, the derivative of log of some f of x of h of theta. Now, you see clearly the advantage of having a model f, which is given by an exponential. Because in our case, this means that what we have is actually delta theta of minus when we do the exponential, and then we have this function which is given by a sum over I over all the nodes of ai, xi, and then we have plus, and then we have j equals 0 up to the number of hidden nodes of hj times bj, and plus the interaction part, which is a sum, a double sum with xi, the weights wij, and hj. So this is the advantage of having log as an exponential. So remember that this is given by e to the minus e of some function x, h, and theta. So that's why Boltzmann machines have been so popular, because you can actually set up, in many cases, analytical expressions, simple ones for the derivatives. And at the end, what we need then, so we need this one in the expectation value calculation, but also the one where we sum over all the data. So if we go back to the calculation of the gradients, so let me just go back here. So if you look at the gradient which we have to evaluate, so we have to evaluate this one, and it's the log of the model. And we have to evaluate this one, which is the same again, except that this one is evaluated as an expectation value. Whereas here, we can just sum over all the stochastic variables which define the input nodes. And we would also sum over the hidden variables. So if you look at these functions, when we are now calculating the different gradients, what we need is actually the gradient. So let me just rewrite it. So I would have the gradient del of L of x of theta with respect to the parameter a. So that means that I would have some d of L and of d of ai. So we would need that one as one of the derivatives. So if we have 100 visible nodes, then we need 100 values of a. And if you now look at the expression which we have, this is simply minus x of I, right? So we have the expression here. And then you will see another derivative which we need, which is d of L of d of, so I'm not setting up the full function. Now I'm just assuming that it's given by this function here, which is not true because this derivative here contains these derivatives. But if I look at, so I should actually have put the log of f here. Actually, this is not correct. So what I should have done here is actually to put in the log of f. This is the function which we need to calculate the derivatives of. So let me be a little bit more precise. Log of f and log of f here. If I do this with respect to b of j, this is simply equal to minus h of j. And finally, we have the last term which we need to look at, which is d of log of f with respect to the weights. And this is nothing but minus xi times hj. So a Boltzmann machine is actually something which gives us very nice and compact analytical expressions. So this is the machinery which we need to encode. So after the break, we are going to discuss one, the basics of Gibbs sampling, which is the way we do this sampling. And one of the reasons for why we use Gibbs sampling, which is defined in terms of what we call the conditional probability, like this quantity here, is simply because if you look at your probability distribution, like this beast which you have here, if I have only 2 visible nodes and 2 hidden nodes, this is something which is easy to evaluate. However, if we are looking at the MNIST data, we are going to have 28 times 28 pixels, which means that this term, if I now use, let's say 500, there will be something like 780 values of x. But there will also be a given number of hidden nodes, because if I just take 2 hidden nodes, this is not going to make a good fit. So in the code, which you have an example of for the MNIST data, I'm using 500 hidden nodes. So with 500 hidden nodes, it means that this guy here is going to be pretty involved in order to calculate directly the probability. So if you're doing metropolis sampling, you will actually sample from the probability. And that becomes extremely complicated and expensive. And that's why Gibbs sampling is the standard way for performing the Monte Carlo sampling. And this is what we will look at after the break. And then we're going to set up the basic machinery, which we need to code the Boltzmann machine. And after that, we can see how we can implement this for, let's say, the MNIST data. So all the equations which you see here, they are also in the Jupyter notebooks, all the derivations. There may be some typographical errors, so let me know if you spot errors. But the reason why I focus so much on these Boltzmann machines is that if you have the basics from these, then you have the basic understanding of how these generative models actually work. So the complexity comes in the way we actually going to generate a hidden layer connection with the visible layer. So the next step after the Boltzmann machine is actually a variational autoencoder, which is a widely used generative method. So before the break, we discussed the basic elements which we need in order to construct our own Boltzmann machine. And the case which we have in the lecture notes is based on a binary. But you will also find the expressions for a Gaussian binary Boltzmann machine. But as soon as you make more complicated probability distribution for your model, then clearly life gets more complicated. Now, what I wanted to do now, first is just to take this intermediate step with the Markov chain Monte Carlo sampling. And I'm just going to essentially give you some of the basic expressions. And I will set up the way you simulate the sampling with a metropolis algorithm. And then we will see from the metropolis algorithm that this actually gives us something which is a little bit more complicated to sample from. And that's why Gibbs sampling is the chosen method for this type of calculations. So keep in mind that what we want when we are performing the sampling, so I'm just going to write this as MC squared, Monte Carlo Markov chain. And what we have is a function which we want to evaluate the expectation value of. So we have an expectation value. And let's just write this in very generic terms, okay? So we have an expectation value of a function. Let's just call this function f of x. And if we think of a continuous distribution, then this expectation value is nothing but an integral over a given domain for the x values of d of x. There is a probability distribution, p of x and f of x. Now, this is approximated by the law of large numbers. So we would have 1 divided by n, and then we have the sum over the xi's. So this is a sum I from 1 up to the number of Monte Carlo cycles, and f of x of I. So this is the typical recipe which is being used. And it means that we are going to pick points x of I, which correspond to a kind of equilibrium distribution. So in order to make this simulation, we use a Markov chain. And the basic mathematics of a Markov chain is now given by the following equation. So I'm sorry for just going very quickly through this. So if you look at the Markov chain, we are looking at the probability of being in a position x of I at a time t. And that is given by a sum over the transition probabilities multiplied with the probability at the previous time. So I'm just going to write this as a sum of where we go from states j. So this could be positions j, xj, to a position I. So this is a transition probabilities. And this is multiplied with the previous probability at the time t minus 1. So you can think of time being discretized. You don't need to think of this as time. But time comes in naturally here. Because when equilibrium has been reached, and you can also rewrite this in terms of a vector matrix form. Then what we have is a vector P at a time t is then given by a matrix multiplied with a vector at the time t minus 1. So this is the basic, as a compact expression for the Markov chain if you're looking at a discretized process where the matrix is finite. And this quantity which we have here, this is the transition probability. And normally, we don't know what that looks like. Or even if we know what it looks like, it can be a very complicated mathematical expression. So this is something which we call the transition probability. And the interesting thing for us is that when this process takes place, after some time, we reach what's called the most likely distribution P, or the stationary state, or the most likely state. And when that has happened, that is when we start sampling. So you can think of a typical process where you need some time to reach this equilibrium, because before you have reached equilibrium, you should not collect this data, because these are data which correspond to not the most likely final situation. So that's why you will often see a parameter which is called burn-in in all these Monte Carlo calculations, which means simply that you simulate long enough so that you have reached the most likely state, and then you're simply jumping in and out of the most likely state. So when equilibrium has been reached, so this is a very short presentation. So in equilibrium, or when you have reached the most likely state, the stationary state, equilibrium, then P of t is equal to P of t minus 1. And then what we have is that P of t, P simply replaced by P. This is a probability we have, is multiplied by P here. So this is our model. If this is a matrix, so since we have expressed everything as a matrix times a vector, so the P then represents the probability of being in different positions, x1, x2, x3, etc. And this is normally called a stochastic matrix, which means that if I sum over it's normalized. So if I sum over all the columns, or I could choose the rows, this is normalized to 1. So P is obviously a probability. So if I sum over all P of I, these are also normalized to 1. So our stochastic matrix has as its largest eigenvalue, as you can see here, which is the eigenvalue when equilibrium has been reached, equal to 1. So that means that the most likely state is connected with the state of this matrix, if you diagonalize this matrix, with a state which has the largest eigenvalue. So the thing is that this stochastic matrix is something which we don't know in general. So you may say, this looks like an impossible task. Now, there is something which is called detail balance. And let me now say something here. Because P, now this W is unknown. So if you look at this W, which is representing a transition from a state J to a state I. So a very simple case where you can calculate this transition probability analytically. If you take a model for the hydrogen atom and you look at the transition, an electromagnetic transition from an excited state to the ground state, there you can calculate an analytical expression for this transition probability. That's one of the few cases where you can actually do this. But in general, this is not known. So that means that what you would commonly do then is to replace this one with a model. And what you will often see in the literature is that this is replaced typically with something which is the probability of making the transition, And this is the probability of accepting that move. Probability of accepting this move. Still, you don't have any idea of what these probabilities are, right? And this is where the principle of what's called detail balance kicks in. So you can set up the master equation for the Markov chain. And I'm just going to set up the final equation. So if you take, so let's now replace this probability with a probability of being in a position I, or state I, if you prefer. Then detail balance gives us a ratio between probabilities. And this follows from the master equation and the Markov chain. So we can now take a ratio between the probability P of I divided by P of J. So the reason why we set it up like this, like ratios, is that this is known. So pay attention to another thing with this known ratio. If you go back to the Boltzmann distribution, which we had, that contains the ugly partition function. Now, the partition function is a constant, is a normalization constant. That means that you're taking ratios where you have a constant, which now disappears in the ratio. So when you take this ratio, the problematic term, the partition function, doesn't appear. So that's one benefit in doing the metropolis sampling, or this kind of detailed balance. This is something which then is given by the probability of making a transition from J to I, multiplied with accepting that probability, divided by the reverse process. Sometimes you have a transition probability which is reversible. So if it's reversible, then these two terms cancel, because then the probability of going from I to J is the same as the probability of going from J to I. That is something which can occur, but in generally, it's not the case. So you will need to evaluate both. Now, the equation, the metropolis algorithm, uses these equations it finds the acceptance probability as the minimum of 1 and the ratio between Pi, Pj, with this multiplied with Tij divided by Tj go to I. So as I said, if it's reversible, then this term just becomes equal to 1, and you just need to look at the ratios between the probabilities. Okay? This is the metropolis algorithm. So I have other courses where I actually derive this in full detail, but now I'm just going to state it, because else we would never end. Now, the point is that we don't use this, and we rather use Gibbs sampling. And the reason why we don't use it is that if you look back at the expression for the probability distribution, this quantity here can be pretty rough to evaluate, because we have many nodes, many input nodes, and many hidden nodes. That means that executing this function every time we suggest a move and calculating the ratio can become extremely time requiring. So we need something else. So you could implement metropolis sampling, but you will see that is a time sink, and it's going to steal a lot of your cycles. So let's go back to the Jupyter notebook, and we are going to look at Gibbs sampling. So let's just do that. And we are going to stay with the Jupyter notebook for the rest of the lecture here. I just need to find my notebook. Here we are. So I use this what's called detail balance, and this is the typical quantity which you want to use. So you can also use other choices. So if this is symmetric, then you end up with Pi to Pj's. However, it gives us a correct recipe for sampling for Mali distribution, but the Gibbs sampling is a simpler rejection-free alternative. So now you're actually proposing moves with the metropolis sampling, but you would reject some moves. Now, Gibbs sampling is a rejection-free way of doing that, and it exploits, as you can see here, the conditional structure of the distribution, which means that you would just look at one of the variables at a time. And it's an algorithm that normally is the one which is used in Boltzmann machine, but it's not only Boltzmann machines, it's used in variational autoencoders, diffusion models, etc. So this type of sampling is the one which is typically used in many of these generative models. Okay? So, as I say here, the efficient way of doing that, so I'm just going to read some of the stuff which you see here. If you now look at the Boltzmann machine, the way we phrased it before the break and last week, this is the equation we need to evaluate, where we have this probability distribution. Now, because this guy here is intractable, this expectation is normally approximated by Monte Carlo sample from the model distribution. So if you now look at this, the sampling problem, suppose you want to sample from, suppose this is a distribution, which is in general a high dimensional space. And this is a problem with the metropolis algorithm, that you need to sample from a high dimensional space directly. So the typical situations, like the Boltzmann distribution in statistical mechanics is one of them, and also latent variable in machine learning, like a restricted Boltzmann machine, which we're looking at now. So the whole thing is that in many important cases, this is known, and this is our case. We know that up to a normalization. We are not interested in the normalization constant here, but we know the model for the distribution. We have fixed it, but direct sampling is difficult. However, the conditional distribution is actually tractable, and this is what Gibbs sampling is about. So we have a target distribution. So suppose this is the target distribution, the way we put it up. So this is nothing but just a plain repeat, and this is the Boltzmann distribution. Okay, so I'm just reminding you of what we've done. So why doesn't the conditional distribution help? So remember now that the conditional distribution, for when, even if this one is hard to sample, if you go back even to the binary Boltzmann machine, you would actually have to evaluate, if you have more than just the simple case with some few nodes, you have to evaluate a pretty complicated function. Well, not complicated, but there are many evaluations. So the conditional probability is actually given by this. And then you use that one to reconstruct the full probability. So it may be easy to sample, and the core idea of Gibbs sampling is that you sample one coordinate at a time from its exact conditional distribution. Okay? So the conditional distribution, like with these Boltzmann machines, as you saw before the break, we actually have analytical expressions for them. Okay? We can really set down the analytical expression based on all the other ones. So we keep all the other coordinates fixed, okay? And then this creates a Markov chain whose stationary distribution is pi, and you have no rejection step which is needed. So the Metropolis algorithm has a test where you actually either reject or accept the suggested move. So if you look at the conditional probability, if you just look, so I just took a case of two variables. So in case you feel a little bit shaky on what the conditional probabilities are. So this is a probability of pi of y, and this is given by this. So we're just using what we defined last week as the product rule and the conditional probabilities. So if you reboot your memories from last week, we then define the conditional probabilities in terms of the probability of finding x and y, and this is given by the product of the probability p of y, which is then given by this quantity. So we're just integrating over x. So if you then look at d dimensions, the conditional probability for coordinate a, given all other coordinates, is actually given by this quantity. Now, this z which you have cancels in this ratio, which is why Gibbs sampling does not require the normalization constant, because the normalization constant is in here, and it's a constant, right? So you see it cancels. That's very important. So you don't need to actually evaluate the partition function, because the partition function, if you have let's say a binary system and you have 100 nodes, you have to sum over 2 to the power of 100. And then if you want to do that properly, it's getting close to the lifetime of the universe. If you look at all the floating point operations. And 2 to the 100 is roughly a baby case. So not having to evaluate the partition function is essential here. So the current state, when you look at the update, so this is the current state of the system, and one full Gibbs sweep updates coordinates sequentially. So you update the first one, you update the next one, etc. And each update, and each coordinate is updated using the most current values of all the other ones. And here I have a two variable example where you have the x and the y, and this captures the essential structure. And each update is exact conditional sampling. The resulting process you can actually prove is Markovian, and the full joint distribution is preserved. So there is an example here where I actually use a bivariate, so that means two variables, Gaussian distribution, So if you go down a little bit in the lecture notes, so I'm going to skip some of these things. You can actually look them up both on detail balance and so on. These are some basic properties. So you can also view the Gibbs sampling as a special case of Metropolis Hastings. And so I just put in these details for the statistics aficionados, in case you want to look into some of these details. But the thing which is interesting for us when we look at the connection to the Boltzmann distribution is simply that what we have, if you look at an X of I, given all the other ones, is that we just have to evaluate this quantity here, and then sum over the xi's here. And that's normally what's called the local Boltzmann law. Update 1 degree of freedom in the frozen field of its neighbors. And the partition functions actually cancels because it enters here and enters there. And that's typically the structure which is exploited in restricted Boltzmann training. You have the conditional probabilities, which we put up before the break, which is this one. And these are just Gibbs updates on the joint distribution. Actually, the probability distributions, which we found before the break, are given by the sigmoid function. If you look back at the equation we had before the break, these are the sigmoid functions. So there are very many nice connections here with these Boltzmann distributions and functions which we have seen before. So actually, I forgot to mention that the conditional probabilities for a node firing or not is a sigmoid when we use a binary Boltzmann machine. That's pretty neat, isn't it? So in a way, with a binary Boltzmann machine, we recover the sigmoid function as an activation function for a given node. So I'm going to skip some more details, but I wanted to tell you when it can be slow. So it's simple. If you have variables which are strongly correlated, then we can have problems. The target distribution is multimodal, can be problems. There's a critical slowing down near a phase transition if you're looking at phase transitions. And these are some basic things. And so why it works, you identify the distribution, you find tractable conditionals, and this is what we have with the standard Boltzmann distribution. These are things you can compute, even if you cannot compute the partition function, or even if you can compute it, it will take too much time. You define a Markov chain by sequentially sampling from these conditionals. Each coordinate preserves the probability, and Z cancels in every conditional. You have respect detail balance. It's also what we normally call ergodic. And there is an example here where we look at a bivariate distribution. So this is a normal distribution of two variables, which we just call for A and B. So this is a probability of finding A and B, and this is the covariance. So one along the diagonal, so that's a variance, and then we have a correlation of 0.5. So this is a very simple function which we can set up. So what we are going to do now is we are going to compare samples which are drawn from the true distribution, which samples which are produced by alternating between the two univariate conditionals. So I'm going to produce a conditional distribution from which I'm going to reconstruct the full distribution. And then we compare that with the one where we sample from the true one. So this is just a pretty simple example where I just use the standard functions which you will have in NumPy. So I have a distribution where the noise is given by, so I just have a normally distributed noise. So that allows us to sample from a mean value and a standard deviation sigma squared. And I'm setting up now you can see now this is my, what I'm plotting here is actually the covariance. And I can set up the conditional probabilities as we discussed before. So this is the probability of F given G here. And I'm setting up, computing the conditional probabilities. I'm setting up the univariate conditionals. And then I do my Gibbs sampling. And if I run through here, you will see these are typical samples. What you see in the background is actually what I produce from the true one. And then if I now sample a bunch of points and see how they compare to those from the original distribution, you will see that it looks pretty much the same. And this is a typical visual test so this is the original one. These are my Gibbs sample. These are the Gibbs sampling path. So you see the Gibbs sample looks pretty close to the original probability. Okay? So it's a way you can actually prove mathematically that you can produce the full distribution by just sampling over one of the events. And this is much faster computationally. And that's why Gibbs sampling is the method of choice in essentially most of the generative methods. And you will see that when we come to variational autoencoders, Gibbs sampling is also the standard recipe because we have to evaluate integrals. When you're dealing with probabilities, the big difference now from these discriminative methods, which we discussed before, is simply that we are evaluating a probability, and that often means that we have to evaluate expectation values. And the expectation value we evaluate for the Boltzmann machine is related to the expectation value of the partition function, which is actually translated into log of the model function. So take a look a little bit about, if you want to read more about Gibbs sampling and so on. So the basic machinery which we have, and this is, now I put a plus here instead of a minus. You can choose whether the energy function has a plus or minus, that's up to you. And if we just skip the minus sign to avoid some clutter, these are the quantities which we calculated before the break. So we have these conditional probabilities and we need to encode them. And when we look at X, a specific H value, we recovered actually that this probability is a sigmoid for the binary model. And what we need when we calculate this divergence is called actually contrastive divergence. So we have the derivative of the loss function. This is the data set. And then we have the expectation value here of the K-step with the Gibbs sampling. So the RVM theory and implementation actually follows next here. So what we need, these are the quantities which we call the one which we call a positive phase, and then the second one which we call a negative phase. And the negative phase is often approximated by what's called a contrastive divergence using Gibbs sampling. And that is covered in implementations which you have below here. Now, what you will find next here, I'm just going to skip some of this because these are things which we discussed before the break, and we have been mentioning these things. What you will find if you scroll down here is actually a explicit derivation of these binary models. So this is the model we have, and we put in the joint probability. So this is what we went through on the whiteboard, and you can see all the derivations. You have also additional derivations. So these are the quantities which we found, and you recognize this as the sigmoids. You will also find the more, a little bit more sophisticated. So in case you have continuous variables, then you can replace the visible nodes. Suppose you want to fit a function, and a function which is defined by X as a continuous variable instead of zeros and ones, or just a binary value. Then you could replace your binary case with what is called a Gaussian binary. And then your continuous variable would then be replaced by this function here, which gives you a Gaussian. If you take e to the minus of that, then you see that the first term would correspond to what you have as a Gaussian. And then you treat the hidden nodes as binary variables. So this gives you a Gaussian binary. Then you can obviously make a Gaussian. You can take other distributions and make more and more complicated models. But it's you who make a model here. Alternatively, you can obviously replace these functions here, as many people are doing nowadays, with a neural network. That's fully possible as well. So you see, you have lots of flexibility in what you're fitting. And the nice thing when you do the Gibbs sampling is that you don't need to evaluate the normalization factor. So what I've done here is actually to add a lot of these details. This is not so exciting. It's just the mathematical derivation so that at the end you have the final conditional distributions for the hidden units, when it fires or not, and you have again a sigmoid here, but a little bit more x comes then in terms of a slightly different expression. Then you can do the same for the visible units, and then for the value x of I given all the h's here. And that's unsurprisingly given by a Gaussian. Okay, so the form of these conditional probabilities, like the last one explained, named Gaussian, and the form of the Gaussian binary energy function. The other energy, you can actually, if you go into this textbook by Foster and go into this, to the GitHub address, you will find an example using TensorFlow where they have replaced the simple binary Gaussian binary with a convolutional neural network. And there are example codes which you can look at if you want to test these features of Boltzmann machines. And there is also a discussion of Langevin sampling, if you're interested in looking at that instead of Gibbs sampling. So this is a pretty novel thing. In machine learning, you know that all these kind of techniques which improve the results, which can speed up your codes, like the way you calculate the gradients using Adams as an algorithm to update the learning rate. These are algorithms which have really sped up the calculations and give you better results in general. And clearly, if you can make an improvements here, this is a field where you will get quite many citations. So the Adams method was introduced in 2014, and it has more than 200,000 citations. A pretty good scientific paper has 100 citations. So we are talking about 3 orders of magnitude more citations. So what I've done here is actually to present a set of codes, which I just wanted to discuss briefly with you. And the first code is actually my own implementation, just using plain NumPy functions. And then there's a PyTorch implementation. And what I'm doing then is actually to, in one case, you have the XOR parity problem, which is a famous test of machine learning methods, whether you can reproduce those data. The other one is actually the two-spin Ising model, where it tests whether the RBM can recover a known physical coupling. So that means that you produce data for energies. If you're familiar with Ising model, I will actually skip this one now because not everybody's familiar with that. But this is a way by which you can actually use a Boltzmann machine to recover the strength or the coupling constant. You could actually replace this Ising model with a model for the gravitational force. And then your Boltzmann machine here could recover the gravitational constant for you, as long as you plug in the right functional dependence, which is given by 1 over the inverse distance between 2 planets. So you could actually give it simulation data on velocities and positions of planets. And then you would train a model which reproduces these velocities and positions, where you would have 1 over the relative distance between 2 planets. And then you could let the Boltzmann machine recover the coupling constant, which in that case is the gravitational constant. So you can use this to actually fit a function in which reproduces the physical laws underlying it. And then, so if you now look at the Boltzmann machine, the first one is actually the binary restricted Boltzmann machine. And what I've done here is actually to encode exactly what we put in the lectures, okay? So the equations, this is the Boltzmann machine. These are the 2 probabilities, the marginal ones. And 0 is just this 1 minus this one, and the same here. And typically this is the derivatives for the weights, and I have similar ones for the other ones. And it contains Gibbs sampling, and it's applied to the XOR data. So we are doing this one. These are the probabilities, same as before. These are the hidden, given, visible, and these are the hidden, given the visible layers, and visible given the hidden layers, sorry. And then we have in Gibbs sampling, we need this one, for the hidden layers. And this is how we update the x's. It will be given by the conditional probability for the hidden ones, okay? So these are the expressions which we put up analytically and derived analytically. And then we have the gradient updates, which we need to set up. So we have obviously a learning parameter. So this eta is the learning rate. And these are the gradient expressions which we need. And the positive phase clamps x to a data sample and uses the exact conditional probability. And that negative phase runs k full Gibbs step to get a model sample x of k. And then it computes this quantity here as H model. Okay? Is that pretty clear? So you will see now that I have replaced that one with a sigmoid. I have a class which is a binary restricted Boltzmann machines. So I need to define the weights. I have the visible biases, and then I have the hidden biases. This is my function. These are the conditional probabilities, and these are the gradient updates which I need to look at. And these are averaged over mini batches. I use a stochastic gradient descent. Actually, you can show that for Boltzmann machines, Adams doesn't do a good enough job. I will come back to that a little bit later. So what follows here, just the coding of these functions. So probability of H given X. So that if you just look at the equations, you can see that the code actually implements the equation step by step. So you have X given H. You have the Gibbs sampling here. This is pretty straightforward. I sample X here. I have the calculation of the expectation value. This is the Gibbs K step. This is the updated for different batches. And you can see the training part, which follows here. And then the evaluation, I have the reconstruction error. And then I calculate this free energy, which I need, and the loss function. So the free energy is actually the log of the probability. So the free energy is actually the log summed over the hidden variables. And so I need this probability here. And then the loss function is actually this contrastive loss, which is actually the mean value which we have here. Then we calculate model probabilities. So let me just rerun this one. And what you will see is that these are the data set we want to produce. This is the XOR gate. So you feed in. So you have only two input nodes. Okay? So, and the input variables are either 0 or 1. And this is a typical output of the XOR gate. And this has been one of the kind, I don't know if you've taken a basic course in machine learning, you have probably encountered why a single perceptual model fails, why a neural network really succeeds in calculating or predicting the XOR gate. So in this case here, we just encode a three-dimensional visible vector, x1, x2, and train the RBM to learn the joint distribution over these 3 bits. So if the XOR is nonlinear, then the RBM needs at least one hidden unit to capture the correlations. And in this case, I have just put in 2 hidden units. So if you have more, then you obviously have more flexibility in the training. So hopefully when you read it and you look at the equations, you see a kind of one-to-one correspondence between the code which I set up and the equations. And then you can set up the training here. I've actually run through this, and I run through this over a given set of epochs. I have a learning rate, which I put to 0.1, and this can be improved. And in my case, after I have a reconstruction error, which is not optimal, this quantity here will oscillate between positive and negative ones, because that's the difference between the 2 terms in the gradient. So that doesn't need to be, ideally, we would like to have this to be 0, but it will fluctuate around 0. I did the same thing. So I'm going to skip this easing model case because I have, because that's more for the people who are interested in the easing model. but that can be seen. But I have an example where I actually do the same thing using PyTorch. And in PyTorch, I have defined a class binary with PyTorch. And it follows the same equation as we had before. But now it uses PyTorch in-baked calculation of gradients. Remember now that the way I calculated the gradients was really in the brute force way. So there is no usage of jacks and automatic derivatives, etc. So that's just the simplest possible way to update the gradients. So in here, what I've done is actually to rerun the same calculation with PyTorch. And you can see again in PyTorch, you define the same probabilities of h given x given h. You sample h, sample x. You have the Gibbs sampling here, calculate the free energy, the reconstruction error, etc. All the same things which we had before. And then I look at the data set. And then if I take the comparison, you will see typically that, so in my numerical Python implementation, plain brute force, actually it stabilizes the reconstruction error. This is the mean L2 reconstruction error. Whereas with the PyTorch, it seems to be going down a little bit more. So I'm actually making a better prediction. This is the free energy loss. And in NumPy, with my NumPy calculation here, I actually have roughly more or less the same fluctuations. But you see now it should be 0, but it's fluctuating around 0. In this specific case, I'm running with a learning rate of 0.05 stochastic gradient descent, and I have 4 hidden nodes. So you can obviously increase the number of hidden nodes if you want to. Now, if you scroll down a little bit more, you will find an example where we, so this is just this easing model where we actually reconstruct the coupling constant. It actually does a pretty good job, both for my own code and the PyTorch one. So the ideal one is this line. This is fed in as input data. But this is not the interesting case. The interesting case is the one which follows here, which contains the training on the MNIST model. And in this case, I'm using PyTorch because it's much more efficient. And with PyTorch, in this case, I have 28 times 28 pixels. So I have 784 pixels. And that's the number of input nodes. So that becomes pretty huge. And if I use a binary, this will be 2 to the power of 784. What you will see is that if you do the training with a Gaussian binary, it's actually going to give a better result. Because now I'm just using a binary, whereas the values of the pixels can actually vary from 0 to 1. So that means that having a binary one here is not the best case. So rather here, if you replace my binary Boltzmann machine with a Gaussian binary, you will get an even better result. And then I have my hidden units. I set up a learning rate, which is fixed to 0.1. I use standard stochastic gradient descent with momentum, and I do something like 50 epochs. And this is roughly what I've done here. So in the binarization here, the pixels are actually between 0 and 1 after normalization, and I actually binarize them with a threshold. So this is actually a problem in this example, which I have here. So I'm running. Actually, this is an important aspect, why you use stochastic gradient descent with momentum and not Adam. So this case here, as you saw also from the previous case with the XOR, is non-stationary, and the negative phase samples xk change every step. Adam, on the other hand, accumulates second-order moments from earlier steps and becomes unstable. So here, the preferred algorithm is actually plain stochastic gradient descent with momentum. The criticism of what I've done here is simply that I'm using a binary because the numbers, the pixels are in 0, 1, but I'm just putting either 1 or 0 if the probability is larger than 0.5 and 0 else. So after training, we run a single long Gibbs chain to burn in from a random binary state. and collect 64 samples with a thinning step of 10 between consecutive samples. And then we display the binary samples directly and not the soft probability, so that the images have the same binary character as the training data. So you can, if you take a look here, I see time is running out. Feel free to take a look at it if you want to. If you in project number 2 would like to explore generative methods, and we have people who actually been writing a project 2 on generative methods and comparing the different generative methods. But you see the basics. I wanted to emphasize a little bit more from a pedagogical point of view, the Boltzmann machine, because that's pretty direct and straightforward to implement if you know the basic mathematical expressions and you implement Gibbs sampling. So you saw my code for this XOR data was not very long. And it's something which one can easily implement. I should also add that all the codes you see here have been revised using Claude. So I had, my problem is that I have tons of codes floating around because every year I add new programs which I write. And then to synchronize it is the boring part. So I wrote a code for this course 6 years ago, and then I wrote a new one 5 years ago, etc., etc. So what I've done this year is actually to use Claude, and then I give Claude all my codes, and then I just ask the agents to synchronize the code and streamline them following my lectures. So it's an extremely efficient tool. It would have taken me something like 3-4 days to do this. And this is done just in 1 or 2 minutes. So all the codes are originally written by me, but I have streamlined them with Claude so that they also follow the lectures more closely. So hopefully you will see the link from the equations and the code directly. So for the remaining part of the course, I will actually do that because over the years, every year I develop new codes, and you know yourself that when you write a new code, it's not necessarily synchronized with what you had before. But if you find inconsistencies between the mathematics and the codes, let me know. These are tools which I strongly, strongly encourage you to use. So me doing this has saved me a lot of time. And it's not the most exciting thing because you just need to proofread things and synchronize it properly. It really speeds up your own work, as long as you know what you're doing. So in my case, I had codes which I believe run correctly. And then I simply just synchronize it. And another thing which, if you look at the graphs here, these are typical graphs which I have improved by using many of these large language models, essentially because previously the way I did it, I would go to matplotlib and I would search through the library there and find the example which I liked, and then I would tailor it to my needs. But now I'm just letting one of these large language models to search the whole library and find the best way to represent the data. So in essence, what I'm saying is update my codes and make nice plots. Well, it's not as simple as that because you have to tell it what kind of plots you want. But many of the plots here are also automatically generated. So I just wanted to say that because I don't want to give you the impression that I'm not using these codes. And I actually say this because I encourage you to use them. Really, I mean, these are tools which make life so much easier because you making a new plot or finding a new nice way of plotting is nice itself, but it doesn't give you any new insights about the problem. But when you write the reports, we obviously want you to state which parts you have used, let's say, large language models for improving your codes. To me also, debugging is so much simpler nowadays. I had in another course I teach, I had a stupid bug. And last weekend, I decided to go through manually, and I wasted the whole weekend on something which could have taken just seconds on running through a large language model. Okay. Yeah. So, I mean, I just wanted to say these things because many people feel, should I use these tools or not? So my advice is use them, but be honest about the way you use them. And be sure that you can assess that the results are correct. That's the most important thing. But to me, this really has speeded up me making the lectures, and hopefully you will see a clearer connection between codes and the mathematics. That is my main aim here, to link properly the mathematics with the codes. Previously, it was not. My original lectures, I mean, you would find different notations in the codes because I wrote the lectures one year, and then I wrote the code next year, and then I forgot about the notation which I used. So this was a long rambling about using these large language models, but the essence is I encourage you to use them, period.